SCAREcrow, Sentinel Conservation via Aerial Reconnaissance and Escort. Yeah, so the idea is that there's wild animals that can be harmful to property. That property can be farmland and whatnot. So in a pandemic era, the last thing you want to deal with is not having an income source as well as food to feed the community. So if we can be able to protect like crops and different property from wild animals, endangering them, that can be really valuable in this type of situation, a pandemic situation. Another thing that comes into play is if the animals are carriers of the disease, can we help maintain animals and keep them out of a certain area that we don't want them to enter? So that area could be a residential area, it could again be like a farm, you don't want them to get in contact with your livestock. So the idea is how can we keep animals away from assets that are valuable, especially during a pandemic. Our approach is different in the sense that, for one, we're pulling on some available data to be able to attack a problem that people aren't necessarily tackling, so the whole identifying and driving out animals. So there's a lot of work where UAVs are used to identify animals, to track animals, to understand what they're doing. There's not a whole lot of work to actually interact with the animal and drive it to do something you want it to do. So one of the things that's different about our approach is we're trying to learn the most effective way to not only track and understand the predict the motion of that animal, but then to actually drive that animal to a place we want it to go rather than just surveilling it. And so the idea there is that we can be able to drive them out of these keep out zones, places where we don't want them to be. Another thing that's kind of unique about that is the way we're doing that is we're assuming emergent swarm behavior of the animals themselves. So it's this idea that the animals are going to do kind of novel path planning as a group. They're going to have some sort of attraction to each other, and then we're assuming a repulsion away from the UAV. So if we can use the UAV to drive a repulsion to those animals to push them away from a certain area, the whole idea of using the reinforcement learning is that we can basically learn a more novel control mechanism for doing that. Especially against these emergent swarm behaviors, it's hard to really understand what they're going to do. So if we can run a bunch of simulations against sort of random and guided emergent swarm behavior, then we can be able to learn more novel control mechanisms for driving them out and guiding them, like herding them in a direction we want them to go.
So when we set out to do the NXPHoverGames 2, we were thinking about a lot of different ideas that were directly related to COVID. We were having a hard time finding a really unique use case other than the typical temperature drone or social distancing enforcement drone, things like that. So we started to look more at other problems that can be related to pandemics. And one thing that is near and dear to us here in the South, specifically in Texas, is the problem with feral hogs. So feral hogs produce rapidly, and they will destroy all livestock and all farmland just to eat and to live. And so they're a real problem here in the South, and so what we set out to do was create a system that would help farmers and ranchers be able to monitor their fields and hopefully keep as many wild animals, specifically feral hogs though, out of their fields to protect their crops. Because the last thing that you want during a pandemic is to wonder where your next meal is going to come from. And as we've already seen with how the grocery stores ran out of food at the beginning of COVID, this is a real issue that we need to be well aware of. So we think this system is the first step in the right direction. So when we first started HoverGames, we put in our idea, and it was accepted for a NavQ flight controller and drone kit coupon. So we purchased the full NavQ board and camera kit along with the flight controller and drone kit. So as far as sensors go, this is currently our setup. We have the GPS on top, we have the NavQ, the camera, the flight controller, and then underneath we're going to add a LiDAR and a PX4 flow. And the reason for that is the GPS, because of its inherent accuracy, or precision rather, the drone is unable to hold a position tightly. And because we're working in potentially confined places with keep out zones for our drone to navigate through, We need to have as accurate of positioning as possible. To accomplish that, we're going to use a PX4 flow and a LiDAR light as a downward altimeter. And what that'll do is give us much more accurate, like to the centimeter accuracy, position hold. So as we command positions from our base station to the drone will be able to navigate accurately and precisely to that position. And we won't have to worry as much about GPS error having too much of a play. Our submission for HoverGames 2 included the use of a thermal camera and an RGB camera. The reason we decided to go that route initially was to be able to operate at night when hogs are most likely to be out feeding in the fields. We didn't end up going that route for the submission just due to cost and the amount of time it would take to develop that solution. We decided it would be more important to get a proof of concept built that works on an RGB camera just due to the ease of development as compared to a thermal camera. There's a whole lot of data out there for RGB cameras and not as much for thermal cameras, so we made that decision based on that fact. Our base station currently only has one single camera. One future improvement would be to do something like stereo vision, so we can actually get accurate depth estimation to the intruders into the keep out zone. That could be done with stereo cameras. It could be done with some sort of time of flight camera. But currently we're using a calibrated single mono camera to be able to get depth estimation that we then translate the X and Y pixel location to X, Y, and Z world location coordinates, and those then can be transmitted to the drone to effectively move the drone to the correct position. On the base station, we are running a Jetson Nano. The reason why we went with the Jetson Nano was because of its GPU support. We needed a high frame rate for our vision processing algorithm as well as our reinforcement learning algorithm. And we decided the Jetson had the most bang for the buck when it came to something cheap but also something powerful. Our software was designed with modularity in mind. For this reason, we have three core components. Our three components are the base station, the agent, and the controller. The reason for these three components are simple. The controller runs the reinforcement learning algorithm as well as our detection algorithm to be able to sense the subjects in the scene and then command the agent based on the reinforcement learning output. That's how the controller works. It communicates directly with our base station. Our base station is essentially a router that's smart. And what I mean by it being smart is it doesn't just take messages like agent move commands and then push them directly to the agents. It first checks that the controller that is sending the command is able to send that command to the agent and then forwards that command on to the agent. So we can enforce things like security and safety within the base station to stop runaway algorithms from potentially crashing our agents, aka our drones, or even going out of our safe area of operation. The agent runs software using Mav SDK to communicate directly via the NavQ board over a serial connection to the PX4 autopilot running in off-board mode. The way that works is the NavQ runs our own code called the agent process, and within the agent process it is listening for agent commands as well as pushing its own position out to the base station. The base station is always listening for agent positions and then forwarding them on to the controllers in the system. This is done by holding a map of controllers in the system, and every time an agent location comes in, it can push out that location to the multiple different controllers that we have in our system. So inherently our system is set up to have multiple components. However, for this project, to keep it simple, we're having one agent and one base station and one controller.
We chose to make the ground station separate from the UAV itself and have them communicate to each other because of the fact that a drone has limited flight time. So these UAVs fly for 30 minutes at a time if you're lucky. There's limited flight time there. But they have the capability of actually being mobile and scaring away these animals from a good vantage point. So even ground vehicles, especially in the train, we're down here playing around in Austin, Texas. and you're talking rocky terrain that's difficult for a ground vehicle to get through effectively. So being able to have that vantage point of being in the sky is really valuable from UAV, but having the power limitation is detrimental. So we have a ground station. That ground station can be provided with shore power, and even if it's on a battery operation system, it takes much less power to operate, and that can be running consistently all the time, and taking information and doing surveillance for the ground operations, or basically the animals that are possibly coming into these protected areas. So that system will be doing the surveillance part of the operation, collecting all the information on whether there's a threat that's entering our protected area. If there is a threat that's entering our protected area, that cues the drone to launch. The drone starts up, it goes out and uses its additional onboard system sensors to provide additional data fusion, but primarily acting on what the centralized ground station is telling it to. And then it's using a reinforcement learning agent for its policy. And that policy that's created by the reinforcement learning agent is how the UAV actually acts, based on the information that is provided from the ground station. This gives us the opportunity to have that vantage point while not being limited by power, and only using the UAV when we need to. The reason why I think reinforcement learning is kind of interesting is it gives us the opportunity to explore that space. So as a human being, we may have ideas of control mechanisms that we would use to herd these animals, but it's still a very chaotic, random environment to try to understand how to control. So a simple like rule-based approach may be difficult to make rules that do well against some of these more novel scenarios, but if we can run a bunch of simulations in a computer to try to sort of characterize those random movements and that like emergent swarm behavior of the threats that we're trying to drive out of a protected area, then we can basically use reinforcement learning to explore that space for us. We don't even necessarily have to use a trained reinforcement learning model, and that's the approach that we're using. But if nothing else, that reinforcement learning agent can help guide us to what kind of things that we should be looking out for, and more effective control mechanisms for driving those threats out of the protected area. So I think that it would transfer well. So I mean, whether you're talking about military domain, the like first responder domain. So I work in search and rescue as well as in the defense, and I think there's a lot of applications where UAVs are being used to target and identify objects, track objects, but then also interact with them. And if you can come up with a way to sort of characterize what a control mechanism would do to the actual threat on the ground or the person that you're trying to find, there may be a way to help guide them out of a situation they shouldn't be in, or guide them into a situation you want them to be in. So I think that there's a lot of application. Anything that interacts with a human being that you're trying to basically drive a behavior out of that living being, that I think this could be applicable to. You identify them, you track them, and then you drive them to do a certain behavior that you're looking for. And I think there's a lot of application in many domains.
So the way we've architected our system is in a way that we can easily extend this to other use cases that follow a similar pattern. And that pattern is, you have an area, you want to have surveillance on that area, and you don't want something to be in that area. The way that we would use our system to help other problems would be by changing out our classification algorithm to be more general or to be more pointed in a specific area, like maybe to search for humans in a security situation. We could also use the behavior of humans, either enemies or friendlies, to then create a more tuned reinforcement learning algorithm to allow the drone to understand where it should position itself to help either the people that it's protecting, or if the people that it is going after are the people it's trying to help, it better can understand how to help those people. So currently our system is set up with a single base station that connects over Wi-Fi to our NavQ board, which then communicates with the autopilot. The reason why we went with that approach was essentially just to make it, again, quicker and easier for development. However, we've built our comms messaging strategy in a way that we could use any type of underlying network, like maybe a mesh network, for instance a Zigbee network, similar to what the Philips Hue lights use in your household possibly, if you have any smart lights. And that system is a mesh system, and what that means is each light in that instance, for that example, each light communicates with its neighboring lights. And eventually they can communicate through their neighbors to get back to a base station, and that base station is the thing that's connected to the internet. And so we would follow a similar approach when we had multiple base stations, what we call our controllers. And we would use the controllers in a mesh network topology, and they would communicate via the base station to a set of drones that were also within that same mesh network. And what that would allow us to do is span over a range within fields, across different farms and ranches, that would be much greater than what Wi-Fi could reach. It would also allow us to essentially chain together to extend out our range versus having to stay within kind of the dome of coverage that Wi-Fi gives you.
I think a big technical limitation is the idea of being able to have multiple UAVs communicating with each other and working together all at the same time. This is a very hot area of research. It's not super well understood yet. There's a lot of work that can be done there, but we have some ideas about how we can be using these centralized ground stations to actually relay information and drive a distributed approach amongst each of the agents on an individual UAV within that entire group, but also sort of semi-centralize it through these ground stations so they have a common environment picture that they're operating on. I think there's a lot of work that needs to be done in the world of intelligent robotics, but being able to at least take a shot at the beginning stages of an agent that can reason in this environment to drive the behavior of a certain adversary or threat in the scene could be a really valuable asset someday. So one of the problems is humans can control and really have a good understanding of reasoning and behavior influencing. The only problem is like a human can only do so much at once. So being able to offload some of that tasking from the human so that UAVs can have some sort of a intelligent reasoning to be able to drive certain behaviors of the adversary is really valuable. Even if we just have a human on the loop, that takes a lot of pressure off the human so they can do all the tasks that they need to do. We automate as much of the extraneous work as possible so the human can do smarter things. As humans, we're very intelligent, very good at reasoning, so let's try to take everything out of the loop as possible so that the human can be on the loop dealing with the most important reasoning aspects of the problem. I've really enjoyed working with the NXP control systems, and I think that this is a relationship I'd like to continue in the future. I think that we can do a lot of great work with some of the developments in the hardware world that these folks are doing.